Okay, so this is part 3 of going over my guide again, so I'm really sorry about that, but we'll hop right in. So we can go ahead and see that everything is going to have dispersion forces. It's also called London's forces or Van der Waals forces. Just be familiar, like it can be used interchangeably in tests or like the ACS. So starting with N2, for molecules that are the same, like O2, N2, like, typically when they are really electronegative, you would think that it was polar, but because polar bonds reside in that electronegativity difference, there is no difference in electronegativity, so I'm just gonna have dispersion there. So when I have NH3, I'm gonna have a lone pair on nitrogen. Guess I'm drawing that somewhere else. So I'm gonna have a lone pair on nitrogen. I'm also gonna have NH bonds, so I create a dipole-dipole and hydrogen bonding. So those are the intermolecular forces present there. Now I'm just circling stuff because why not? So for carbon monoxide, carbon and oxygen have a polar bond. So I have a polar molecule there. When I have like CO2, for example, which does have that polar carbon-oxygen bond, it's canceled out because it's linear, because I have carbon double bonded to 2 oxygens. So despite that having a polar bond, it's going to have dispersion forces, making it not polar, right? So here's just more explanation. I guess I'm just drawing out carbon monoxide and explaining the CO2. So that's exactly what I just said. The double bonds are linear, so it's going to cancel out. So it's going to be nonpolar. So for CCl4, I would think, carbon and chloride would be a polar bond. It's tetrahedral. It's all the same bond type, so it's going to cancel out, so it's going to be nonpolar. So that one is also just going to have dispersion forces present. Alright, so moving on, we have a phase diagram, which I love. Phase diagrams are the best thing in the world. So A is saying if I start on the line from B to C, which is just the line that's running between liquid and gas phase, if I start on the line from B to C and increase the pressure, fusion will occur. So that's saying if I increase my pressure going up, that fusion will occur. But I know if I go up from this point, I'm going to have condensation, right? The change from gas to liquid. So I know that's false. So B says if you start on the line from B to D and increase the temperature, sublimation will occur. So that's going to be my line there. If I increase temperature, I'm going from solid to liquid, and that's fusion. So I know that's going to be false as well. Alright, and then for C, to figure out what is the densest state in a phase diagram, you're going to want to start at that triple point. And when you start at that triple point and increase pressure, I don't know what I'm going to right there. So that's just saying fusion would occur if I decrease temperature, if I go to the left, right? Because I end up in the solid state. So for C, well, anyways, my arrows are just saying be able to like know what's happening when I go from the triple point or increase pressure, increase temperature. So C is my densest state. Because if you start at the triple point, I increase pressure, I'm naturally going to go to the densest state because I'm pushing down, and so I'm forcing the molecules close together. So the reason why, liquid water is its densest state, because usually you would think solid, but the lattice that it has with water creates it to be less dense. It's the same reason why a soda can will explode in the freezer, because the solid will expand as it freezes. So just be aware that for phase diagrams, this densest state is going to vary based off of the shape. Like for this one example on the left, I increase my density and I end up in the solid state there. So for these next problems, don't worry about them. I'm going to make a separate video going over them at some point in the semester because it's not really like focused on, but just keep those in mind because the ACS will ask on them. They love to. 25, we're given information about a solution, which the following pieces of information could be true for this to occur. Solvent-solute interactions are greater than solute-solute, and solvent-solvent interactions, and I know that's got to be true. That's saying that the solute and the solvent are more attracted to each other than they are to themselves, and if that's the case, then they're going to want to mix, right? So I know that, yes, that's going to be true. Okay, if I look at solvent-solute interactions are less than solute-solute and solvent-solvent interactions, then why would they want to mix? Why would they want to form a solution if their interactions are weaker than their own like interactions with themselves? So they're going to remain separate. And then C, solvent-solute interactions equal solute-solute and solvent-solvent. So yeah, so they're just naturally going to have a tendency to mix. So if it's greater than or equal to, that's when I know a solution could form. So for this, the answer is going to be E, which is A and C. Okay. And moving on to 26, when I see like which of the following is most miscible with methanol, most miscible is going to be what's going to have the most common intermolecular forces. So like dissolves like. So I'm going to look for something that's going to have, well, obviously dispersion, but dipole-dipole and hydrogen bonding as close as I can to that. But when I look at these answer choices, I don't see anything that has hydrogen bonding, even though I mean technically an oxygen can hydrogen bond with another molecule, but regardless, I think that goes beyond the scope of this class. So I would be torn between A and C, but when I look at C, I see it's higher in molecular weight, but an A is smaller. So in this case, I'm going to want to go with A because when I have C and I add those carbon chains, right, I'm decreasing the hydrophilicity of the molecule and making it more nonpolar the more I add like these nonpolar like methane groups on it and these alkane like carbons, right? So 27, the heated solution is negative. What can we conclude about the magnitude of H solute and H hydration? So delta H of the solution is equal to delta H solute plus delta H hydration, right? So the heat of solute is just going to be the heat required to separate the particles from one another, and to do so I have to add heat, right? So that's got to be endothermic because I have to add heat to separate them. They don't want to naturally separate, so I have to do it myself, right? So my heat of hydration is the combined term of the heat of solvent and heat of mixing. So this term on its own is going to be very very exothermic, right? So I'm giving off heat. I'm forcing particles together. I'm forcing them to give up space. I'm forcing them to make new interactions, right? So that's going to be a highly exothermic term. So if my delta H solution is negative, that's going to tell me that my negative term is larger. So it's going to say that my delta H is going to be greater than my H of solute, right? So it's going to be A, my H of solute is small, and D, my H hydration is large. So the answer here is F. Moving on, if the absolute value of H solute is greater than absolute value of H hydration, what can we conclude by the energetics? This is saying if my endothermic term is greater than my exothermic term, what is the overall going to be? And I know it's going to be overall endothermic if the endothermic term is bigger. So don't get tripped up on that. 29, when I add additional solute to a solution, does it not dissolve? What does this tell us about the solution? It is unsaturated, saturated, or supersaturated. So if it's unsaturated, when I add more solute, it'll dissolve. So, yeah, I mean, that's all I can really say there. If it's saturated, it won't dissolve, and if it's supersaturated, it's going to recrystallize. So I'm just go ahead and writing all that stuff down for you guys right there. So, if the question had said, like, if I add solute and I notice, like, crystals forming on the bottom, that's when I know it's going to be supersaturated, right? So the book has good examples of that. 30, which of the following is false? Increasing pressure increases solubility. Yes, this is true. I force them down, I force them to mix, I force them together. Yeah, true. Increase the temperature increases the solubility of solid. Yep, think about that yummy iced coffee. When you put that sugar packet in there, it doesn't really mix, and sometimes you have crystals at the bottom. But when you have hot coffee, you're always going to have, your little sugar crystals dissolved, right? So increased temperature, increased solubility. However, the opposite is true for gases. So I know C is going to be my answer here, or C is false, because I increase the temperature, I decrease the solubility of a gas. So think about when you have like a soda can, or not, I guess just like a soda, and you leave it outside, it has like carbon dioxide bubbles in there, and as it gets to room temperature, those carbon dioxide bubbles begin to bubble out, right? Because their solubility is decreasing. So here's me just drawing a little soda, here's little CO2s. As you leave it out, they're able to leave, right? Because they decrease solubility. Alright, so 31, what pressure is required to maintain a solubility of 0.15 carbon dioxide when the temperature is 25 degrees Celsius. So for this, you're using Henry's law, which is solubility equals KH times pressure. So if you're ever unsure, like I was just for a second, just look at your units for KH, right? It's molarity per ATM. So I know I'm going to have to multiply by pressure in order to be left with molarity, because solubility is has the same units for molarity. So I plug in what I have. I have 0.15, which is my molarity. So I have 0.15 equals that KH is a 3.15 or 3.4 times 10 to the negative 2 times pressure. And so when you divide, you get 4.41 ATM. And I believe this was one on the key that was incorrect. So there's my sad face, or half smirk face, for being kind of sad there. So moving on, 32 says a 500 milliliter sample of pure water is allowed to come to equilibrium with pure oxygen gas at a pressure of 755 millimeters mercury. What mass of oxygen gas dissolves in the water? The Henry's law constant for the oxygen gas is 1.3 times 10 to the negative 3 moles per ATM. So for this problem, once again, you're going to use the same equation. Oh yeah, that's me apologizing in advance for 33. Sorry about that. I sat and stared at it for a little bit today. So for this one, I'm going to use Henry's law. So what I'm going to do is I'm going to find molarity, right? I'm going to find that solubility, and then I'm going to take that molarity, plug in volume to find moles of the solute, and then I'm going to convert moles to mass of oxygen gas. So this was another one that was incorrect in the key, because I think I put D, but you should have gotten C, but someone also said they got D with the answers from C. Anyways, it's either going to be D or C. I don't think your test would have something that's crazy or like that close like that, or would specify the formula, but oxygen gas is diatomic, so it's going to be an O2. So for this, I need to first convert from millimeters mercury to ATM, so divide by 760. Plug in what I have to find molarity. I multiply that to get 0.0025. So then I plug that into the equation for molarity, which is just mole solution, moles of solute over liter solution. So 0.0025 equals X amount of moles over 500 milliliters, which is 0.5 liters, because it needs to be in liters in this case. So when you plug that in, and then you multiply by the molecular, or the molar mass of oxygen gas, I got 0.041, but someone else has also gotten 0.021. So whatever you get, it's okay. It's not that big of a deal. There was something lost in translation here, so kind of a goofy question, but that's A-okay.